Thank you very much, Professor. So my name is Tetsu Ichitsubo from Kyoto University, Japan. So now I am working as a Professor Egami at UT at Knoxville. So I am not good at hearing the English. So if you have a question, so please speak more slowly. So today I'll talk about static heterogeneity due to the elastic inhomogeneity in the metallic glasses. So my collaborator is Kato Hideni, Kato, and Abe, and Biwa, Hosokawa, Matsuda, and Saida Baron Matsubara. So present in my talk, so I like to present experimentally the static heterogeneity in the metallic glasses. So first, so the content is this. So firstly, I like to talk about the beta relaxation. So beta relaxation detected. This is can be detected by ultrasound, and which leads to the crystallization. So by the stochastic resonance phenomenon. So and then the from this phenomena, so I proposed static heterogeneity of glasses, and so in order to reveal and validate this model, so we have used the employed the two methods. One is ultrasonic sound velocity measurement, and the other is inelastic X-ray scattering measurement. We have studied the phonon behavior of submetallic glasses, and I like to address structural view of glass transition. So so we introduced some recent results from the others. And the most I want from you, so is I like to have some theoretical idea from you. So please give me. So what is a metallic glasses? So metallic glasses are defined as amorphous alloy that exhibit reversible glass transition. So the metallic glasses have attractive characteristic features in technological viewpoints. So high tensile strength and relatively low elasticity and high corrosion resistance they have. And not only from the technological viewpoint, but also the scientific viewpoint. So this is very attractive. Why metallic glasses are so stabilizing? So this is a very simple question, but this is not solved yet. So this is kinetically and thermodynamically is under debate. And how is the structure of metallic glasses? So this is based on the Professor Miracle. So structural model proposed by Ivan Ma and based on the Professor Miracle. So this is so metallic glasses is believed to be homogeneous. But recently we and the other researchers proposed inhomogeneous. So and so usually the glasses shows the several kinds of the complicated relaxation phenomena. So one is alpha relaxation. This is very well known. This is a dynamic glass transition. So this time scale is 0.01 and 1 second and etc. So the typical frequency is of the order 0.01 hertz or 1 hertz. So and so this is typical. There is a typical relaxation phenomena, so-called slow beta relaxation. So beta relaxation is not well understood to date. So beta relaxation, so-called Johari-Goldstein beta relaxation, is not so well understood. So Johari proposed that the beta relaxation occurs in the very, very local relaxation. So but the other person claims that the homogeneously occurs, but this is not well understood. And fast beta relaxation exists in some, for example, mode coupling theory or etc. So in the liquid science, the fast beta relaxation or mu relaxation is very important. So, the objective of this our study is we try to investigate the correlation between the glass structure and relaxation processes.
Can you say a bit more about the distinction between the slow and the fast beta relaxation?
Yes. This is so-called this is Johari-Goldstein beta relaxation, which occurs atomic jump due to the atomic jump. So the with the activation energy. So, but in the case of the fast beta relaxation, this is considered to the rattling motion of the using the probably cage in the glass. Okay, please.
So then, how is slow beta related to alpha?
Alpha, yeah.
Sorry?
What's the difference between slow beta and alpha?
Alpha relaxation is cooperatively relaxation process. So, for example, typical time scale is almost 1 second, but this time scale is not more fast. So faster. For example, 100. I'm sorry. So 100 hertz or 1 kilohertz or etc.
But yeah. So this. I guess I'm just a little confused with this. So alpha, you said, is a cooperative motion of matter.
Yes, cooperative motion.
Slow beta is an atomic motion.
Atomic motion. Yes.
But since there are no large holes or vacancies in the structure. Any site change has to be a cooperative motion. So again, I'm not clear what the difference is between the slow beta and the alpha. It seems to me that they both have to be cooperative in some sense.
Okay. We don't know yet.
Okay. So usually this figure shows the typical temperature dependence of the elastic constant of the amorphous alloy. So the elastic constant decrease with increase in temperature, and they continuously changes around the glass transition temperature. And at the crystallization, so they rapidly increases like this. So this is the typical transition typical temperature dependence of the elastic modulus. So, but recently, so in the process of measuring the temperature dependence of the elastic constants, so elastic constants increase suddenly under the ultrasonic vibration in the range of the megahertz frequency range. So we have found that the rapid increase of the elastic constants around the glass transition temperature, we have found that this phenomenon. So this abrupt change increases is due to the crystallization behavior. So
sorry,
yes?
What are we looking at here? What are you showing on the graph? What is the frequency shift?
Yes. So yes, this is the frequency shift. Therefore, this is the elastic corresponds to the elastic constant. Yes. And this is the temperature change of the elastic constant.
So if you don't have this ultrasound, it crystallizes at 670 or something, yeah?
Yes, it's okay.
What kind of measurement is it? Is it spectroscopy?
Yes.
No, ultrasonic.
Ultrasonic spectroscopy method. So like this, like us. So there are some other some researchers have reported similarly. So in the case of Kosterlitz, so the effect, he had proposed the effect of the radio frequency magnetic field on the crystallization of the ferrous magnet. So radio frequency RF magnetostrictive vibration is responsible for the acceleration of the crystallization. So for example, Gupta reported that ultrasonic vibration enhances the crystallization of the iron-based amorphous alloys. So these phenomena indicate that the structural stability of metallic glasses is deteriorated under the dynamic external fields, even at relatively low temperature. So below the glass transition temperature. So this is one topic of my talk. So what is the mechanism of the deterioration under the ultrasonic vibration? So this figure shows the the typical character of the metallic glasses that is rarely observed the other types of glasses. So Tx means the crystallization temperature. Tg is the glass transition temperature. So intriguing so in this figure, this figure shows the DSC profile of the obtained for the zirconium nickel metallic glasses. So zirconium nickel, so of this composition, usually doesn't show the glass transition temperature at the usual heating rate. For example, 40 Kelvin per minute. Therefore, these are so-called amorphous alloys, not so metallic glasses. But when the heating rate is rapidly higher, so becomes higher. So for example, 500 degrees centigrade per minute. So we can observe the glass transition phenomena before the crystallization temperature. So because crystallization is due to the atomic jump, is caused by the atomic jump. But when we rapidly heat of the sample, the crystallization is very, very retarded at the high temperature. Therefore, the metallic glass transition can be observed. So this is Tg and Tx versus heating rate dependent. Okay, so this is a TXTG and of the palladium, nickel, copper, phosphorus metallic glass. This is the most stable metallic glass. And zirconium, copper, zirconium, nickel. So usually the Tx is always over the Tg, higher than Tg. But in this case, Tx merges Tg at a certain heating rate. So this is a typical feature of the amorphous, so-called amorphous, conventional amorphous alloys. So crystallization, this is very interesting for me. So because kinetic freezing occurs. Kinetic freezing occurs below around the glass transition temperature. Therefore, with respect to the alpha relaxation. Therefore, below the glass transition temperature, so most of the kinetics is frozen. But beta relaxation or faster mu relaxation or fast beta relaxation is still alive below the glass transition temperature. Therefore, so such a crystallization is probably maybe caused by the beta relaxation. Because atomic motion associated with crystallization below TG appears to be motion associated with the beta relaxation.
Do you think that's related to the colloid experiments in Edinburgh, where they've seen colloidal crystallization out of a glass?
Colloid, I don't know this colloid crystal.
They also seem to find that that if the glass is very dense, so the alpha relaxation died out a long time ago, there are very small displacements actually sufficient to induce crystallization, and that's what seems to be allowing the glass to crystallize.
Well, you have these two curves crossing. You don't have any data points in the range in question. Is this convincing?
Is this?
Yes.
So, therefore, but this is just only extrapolation. Therefore, so this cross point is tentative point. So, for example, because this curve behavior is we don't know this curve behavior. For example, for this. So probably Professor Wang is very familiar with this figure. No.
Can you not check this in slow cooling?
Heating.
But if you did slow cooling, you would see the TG first,
the
right?
dependence of the TG and on the heating rate or the cooling rate is not so sensitive to the TX. So that's true. This is the experimental observations. For example, we can measure the TG and the TX by using the ESC thermal analysis. Normally, the TX is more sensitive to the heating rate or cooling rate.
But I think the question is, couldn't you measure these by cooling instead of heating the DSC?
No.
Yeah, but if you go to high temperature, it crystallizes.
Normally we use heating, change the heating.
This TG and TX were observed by measured by the heating process.
The difference in slopes between TG and TX, isn't that sort of a manifestation of the different activation energies?
Yes. Apparent activity. So the slope is inverse of the apparent activation energy. So actually, so we have this is reported that so beta relaxation is usually observed firstly. So in this system, palladium nickel copper phosphorus system by Peltier, Dr. Peltier. So this is a dynamic alpha glass transition, and this sub-peak is correspond to the beta relaxation. So beta relaxation is occurs so far below the glass transition temperature. So this measurement was performed by the 1 Hertz, very low frequency. So therefore, they performed this by using this 1 Hertz spectrometer. So therefore, the TG is correspond to the calorimetric TG. And so Peltier have evaluated the activation energy of the beta relaxation and the relaxation time like these values. So by using these values, we have recalculated the internal friction by using the beta relaxation. So for megahertz frequency range. So in our experimental measurement frequency range. So this is recalculated figures of the internal friction of the beta relaxation. So So this is the yellow region is indicated the glass transition of the palladium nickel copper phosphorus metallic glasses. So 0.1 megahertz and between the 0.1 megahertz and 8 megahertz frequency between the. So we can clearly we observe the increase of the beta internal friction around the glass transition temperature due to the beta relaxation.
What's special about megahertz frequencies for these atomic glass? That it seems fairly fast.
So because so this is usually glass transition temperature around the glass transition temperature. So the atomic motion is very very fast. So if the atom can move, if there is a region, so where the atom can move there, so they. So Peltier derived that from his experiment, he has derived the activation energy E and relaxation time.
This is an activation energy for one atom?
Yes, one electron, one EV. So therefore the too small. So but so so yes. So yes.
Not single atom.
Yes. Single atom. So
on some process.
For some process.
Yeah.
More the beta
beta
relaxation.
Yes. This value is a very common value for beta relaxation. So Hoso Chen et al. So reported this value for several metallic glasses. Probably process around.
But they claim the value is the active energy of the slow beta relaxation.
So this is an activation barrier associated with the beta relaxation as distinct from the alpha relaxation?
Yes.
Yeah.
Yes.
It's not just one value, you have a distribution of this.
Yeah, probably. So usually, in the case of alpha relaxation, the activation energy is probably 5 or 10 electron volt EV.
Per atom or
No.
for the whole process though?
I'm sorry.
Yeah, so I mean 1 electron volt is not unusual. I mean this is typical for example, atomic diffusion in crystals.
Yes.
1 electron volt
Yes,
per atom.
two or three, because
Well, it depends on the process.
Yes. So I remember that. So in the case of the interstitial diffusion process, so this in that case the activation energy is almost this value. So okay.
Can you say very briefly what you mean by internal friction and how it's related to G double prime over G prime? Or something?
I'm sorry. So G prime means storage elastic modulus, and G2 prime. G2 prime means this is the internal friction. So the loss modulus. So the imaginary part of the.
It's related to G prime, GU, G.
I'm sorry. So this is the G prime. So the elastic constant decreases towards the glass transition. And the G2 prime increases. So
Q inverse?
Q inverse means so this is a correspond equivalent, almost equivalent. So the definition is.
Right, but what is Q inverse? It's the ratio of the.
Yes. Sorry. So. Almost. Okay. So we have observed the internal friction of the palladium nickel copper phosphorus metallic glasses by using the 0.4 megahertz like this. So we go to right. So the Q inverse internal friction increase like this figure. So this is a recalculated result So this region is this figure is very similar to this region. So therefore, we have concluded that the increase of the internal friction means that the periodic ultrasonic strain is resonant with the atomic motion. So it is considered that the atomic motion of the beta relaxation can be responsible for the ultrasonic induced crystallization of bulk metallic glasses. So in the case of zircon copper nickel aluminum metal glasses, the similar phenomena is observed. So the internal friction increases, and the crystallization occurs in this case. So this is the summary of the three metallic glasses. So internal friction increases around the glass transition temperature, and then the crystallization occurs. So the beta relaxation is when we assume that the beta relaxation activation energy is about 1 electron volt. So the beta relaxation of the metallic glasses around the glass transition temperature is almost 1 megahertz or etc. 1 megahertz. Therefore, under the ultrasonic vibration of the 1 megahertz frequency range, the structure that is very sensitive to the megahertz frequency range of ultrasonics. So this is a result obtained for the palladium nickel copper phosphorus metallic glass. This is the most stable metallic glass in the world. So when we annealed this sample below the glass transition temperature, slightly below, just below the glass transition temperature, for 18 hours with under the ultrasonic vibration. So we have the crystallization. We have found that the crystallization occurs like this figure. So after that, DSC signal indicated no crystallization heat, no heat. Therefore, the sample was fully crystallized. But when the sample was annealed without the ultrasonic vibration, so it keeps pure amorphous alloys. So this, for example, so after annealed at 219 degrees centigrade for 74 hours, very much more longer, but without ultrasonic vibration. So it keeps pure amorphous alloys. But this is the ultrasonic vibration is very, very sensitive to the. So the structure is very sensitive to the ultrasonic vibrations. So, in the case of only 10-hour annealing, so what happens? So probably, so we can imagine that the partially crystallized occurs, partially crystallized. So DSC indicated that so slightly the crystallization heat is slightly decreased because I'm sorry. So free crystallization heat is 36 joule per gram, but in this case 29. Therefore, the partially crystallization occurs. So, which part in the amorphous matrix are crystallized under the ultrasonic vibration? This is a very interesting question. So this is answered. This figure is observed by TEM, transmission electron microscopy. So this amorphous-like region is colored gray for visualization. So this is this lattice contrast, fringe contrast is indicates the crystal. But this is amorphous-like. So the isolate usually when the sample is crystallized at the normally, so above the glass transition temperature, so very large, 1 micrometer of size. So a very large crystal is initially formed. This is a typical characteristics of the palladium metallic glasses. But in this case, only several nanometers crystallization occurs. So the isolated amorphous islands are surrounded by the crystallized regions. Although usually, this is isolate. Although usually an isolated crystalline particle is formed in the amorphous matrix.
I have a question about this.
Okay.
Maybe this is just a non-representative area, but when I look at this microstructure, it looks like maybe half of the material has crystallized. But when you look at your enthalpy peaks, you went from 36 joules per
yes.
20. So
Okay.
it looks like you have more crystalline space here than would be suggested by your...
Yes. This is this structure is typical, but so in the wide range. There we have found that no crystallized occurs in some part. So therefore, this structure is also homogeneous. So okay. Yes.
Very naive question. In oxide glasses, it's rather usual to observe crystallization just after phase separation took place in a metastable state. Is it possible that some kind of phenomenon also happen in metallic glasses?
So this is a very serious question. So I don't have as an exact answer, but okay. So this yes, it depends on the system. But in this case, so the compositional fluctuation we have not yet determined. So. But this is a very interesting question. So, but
phase separation has been seen in similar glasses, palladium-based glasses. So it is possible.
It is possible. Okay.
When you, sorry, just at the bottom of that slide, you say usually an isolated crystalline is forming them all. What do you mean by usually? This doesn't look like the usual situation?
Yes.
So what's usually in other materials?
Usually means normal crystallization without ultrasonic vibration.
So the morphology of the crystal.
Morphology is this. So this is 1 micrometer size. Very different. And so I'm sorry. So this is skip. So from the observed microstructure, so experimentally, so we have we have proposed heterogeneous structure like this figure. So it is considered that the crystallization at a low temperature, just below TG, is strongly related with the beta relaxation, whereas the atomic motions are stochastically resonant with the ultrasonic vibrations. In the region where the crystallization occurs, intrinsically the atomic mobility is high, density is low, and elasticity is soft. From this viewpoint, we infer structural model as shown below. So this is so the yellow part is a weakly bonded region, and so this is a strongly bonded region. So like this, this is a static heterogeneity of this metallic glasses. So this structure's feature is already percolation is already present in the glassy state. So, but probably, so Professor Egami is not does not agree with this. But, sorry.
I questioned your choice of intrinsicness of the phenomenon, because I mean a crystallization is a rare event, and it could be related to a local random fluctuation, but it doesn't necessarily mean that the entire region is more mobile necessarily, because once you start crystallizing, you have a more compact phase that arises, and that itself can fuel the extension of the crystal. So it doesn't necessarily reveal that there is an intrinsic heterogeneity in the structure.
So usually, usually, so at this temperature, so crystallization does not occur. So without ultrasonic vibration. So with under the ultrasonic vibration, stochastically resonant atomic motion under the ultrasonic vibration. So that leads to the crystallization. So in that case, so this is intrinsically.
The ultrasound can nucleate crystals.
That's exactly my question.
But then it can grow a little bit.
Yes. So that yes. So yes, okay.
I guess the previous question was by how much does the crystal grow? I mean, there could be a tiny low density region which the ultrasound triggers, and then it grows into a much larger crystal. Right. So can you really infer the size of the original region?
Yes. Original region, I can't determine. So, but so probably this point. So therefore, so probably percolate only. Percolation structure is maybe not essential, but probably. So this is this can't be directly from this structure derived from this structure. This is just image, intuitive image of the from the based on the basis of the thermodynamics behavior. So, but
it's a misleading image in the sense that you draw it as percolating, and there's nothing about the phenomenon that.
Just as a simple suggestion, have you considered doing the same experiment but stopping it after 5 hours or 2 hours? And then that would give you an idea of nucleation, and that you can decouple the nucleation from the growth.
Yes.
To see how this. How this is.
Okay, so it's a very good idea. But
also for people who are experts, how much is if suppose you didn't use ultrasound to nucleate, but somehow you got nucleation out of an amorphous phase rather than a liquid. What's known about the morphology of nucleating crystalline droplets?
Well, so I think you mentioned already, typically you have an isolated event that grows even in amorphous aluminum alloys where you get crystalline nuclei about this size, 5 to 10 nanometers. They're clearly distinct from one another. Okay. And they're completely surrounded by an amorphous region. So it's an isolated nucleation event and then growth. And then in fact that becomes stable because you get solute rejection that stabilizes the growth. When you have two growing particles, they sort of stop before they get to each other. So this is, I think, a rather unusual.
Yeah, it is unusual.
Okay.
But two things are going on. One is the dissipation of energy applied by ultrasound by this central Q-1. And then this dissipated energy becomes heat and then crystallizes. So these are not necessarily the same thing. So they are closely related, but I have trouble with asserting that this region represents a soft region.
Somewhere in there was a soft region.
Yeah, somewhere. Exactly.
But we don't know if it's the whole region or some very small subset.
We don't know.
So we don't know, but okay. So but Okay, so let's go next. So the reason why I propose is that structure model. So I like to explain the marked increase of the elastic constants after the crystallization. So usually the elastic, for example, the shear modulus of the metal glasses is very, very small in comparison to that of the crystal. So in the case of the after the crystallization occurs, so the shear modulus increase 5%, about 5%, 50%. So very, very large elastic constant change occurs with regard to, despite the fact that the density change is only 1% or 2%, 0%. Yes. So very small change, but density change, but the elastic constants drastically change, for example. So in order to explain this phenomena,
Can I interrupt for a second? So that's quite general. My impression, I haven't read the literature on this very much, but my impression was that the elastic properties of the amorphous glasses were typically about 10% less than.
No, 25%.
So it is 25 to 50%. Yes.
Yes,
50 for the shear modulus. And
No. I mean, he divided the change by amorphous. So if you call crystal 100%, it's 100%.
Yeah, that's right.
Anyway, 25 is about right.
Is that an unusually small density change?
No?
actually, it's kind of big for metallic glass.
Okay. Usually 0.5% or less.
So in order to explain this so large change, we have proposed this softer like this model. So this model is SBR, strongly bonded regions, surrounded by the weakly bonded region. So weakly bonded region, when the SBR is surrounded by the WBR, so macroscopic elastic modulus becomes very, very soft. So for example, this is the WBR elastic constant, and this values. I'm sorry. So this position is only 100% SBR. When the WBR fraction is only 10%, within the 10%, the elastic constant decrease like this figure. So therefore, only 5% or less than when the WBR, the fraction is only 5% or 10%, the elastic constant decrease like this.
I'm sorry, maybe this is a silly way of thinking, but could you back up a slide? So you're arguing that there's something unusual, yes, going on because we get such a large change in elastic properties with a small change in density. But that's not unusual. Think of an elemental metal, and I can change its volume by 5% and change its elastic properties by 100%, and I'm thinking about melting. If you take pure elemental metal, and then melt it, you increase its volume by about 4 to 6%, but its elastic properties go to 0. So is this really unusual that you get a 20% change in elastic properties for a 2% change? I mean, is that unusual? Am I looking at this wrong somehow?
So you said that you mean that the transformation, liquid transformation.
Well, you're implying that this is unusual, that the change in elastic properties, 20-30%, is really, really big for a density change of only 1 to 2%. But I'm asking the question, maybe that's typical.
That's right.
Because you take a crystalline metal and you melt it, you change the density by only about 4%, so not a whole lot more than that. And you change the elastic properties 10 to zero because it becomes a liquid. It's got no shear modules. So maybe this is not unusual.
That's right. You are assuming that the density change is only 1 or 2%, therefore that the portion of the structure which changes also 1 to 2%. That's not true. Right?
Probably.
And so it's an important question because what you're trying to do is to take this idea and say that there are some local regions that are really inefficiently bonded, and maybe that doesn't follow from this line.
That's right.
I think this is worth thinking about a little more carefully.
Yes.
No question.
So, okay. So, on the other side, so the WBR is included in the SBR matrix. So the elastic constant decrease almost linearly. So therefore, this model, I think that this model cannot explain this drastic change of the elastic constant. No. This one. Okay. But okay. Yes. So.
Well, that can only not explain the data if you presuppose that because the density changes in the strongly bonded regions is small, the elastic properties there cannot change significantly, which is sort of what Dan was asking.
That's right.
I think it's only given the assumption that somehow all the density, all the modulus change has to come from these weak regions, then you can argue it has to be the thing on the left, but that's not so obvious.
So it is difficult to measure such a WBR fraction.
I'm trying to connect up what you said here too. So is that you're trying to explain both the change in the elastic constant, the small change in density, and the morphology of the nucleation to say this has to be some kind of strong regions surrounded by percolating weak regions? Because taken just the elastic constant, then we're saying you don't need that.
That's right.
But so are you trying to explain multiple phenomena by sort of coming up with this picture of strongly bonded surrounded by weakly?
If you assume, we need more experiments.
Yes, okay. So
actually, let me just interrupt with a completely different idea that, in spite of everything we've said, that supports this idea. We think of crystalline metals as being more efficiently packed than metallic glasses.
Yes.
That's true on a global scale, but not on a local scale. Locally, metallic glasses are probably more efficiently packed than in their crystalline counterparts. So if you have some regions that are more efficiently packed than a crystal, let's see, how do I say this without sounding confused? But globally, it's less efficient than a crystal. Then that means there must be some regions in that structure that are a lot less. So it does support this idea that there are strongly bonded regions and weakly bonded regions. Whether the strongly bonded regions are surrounded by weakly bonded regions or not that's a separate matter. But the idea that there are some regions that are very efficiently packed, more efficiently packed than in the crystal, and other regions that are much less efficiently packed, I think that has some validity.
Exactly. So heterogeneity is the idea, right?
Yeah.
So if you don't push it too far, then it's very important.
And so we can discuss the particular approach you've chosen to support that idea, but whether the approach you've taken is valid or not, I think the idea has some merit.
Exactly. Details are separate matter, okay? Ideas is important.
That's the major question. So the major question is what's the distribution and what are the length scales and what are the structural manifestations of that?
Separate matter.
Separate matter. It is different kind of measurement. But ultrasound cannot do that.
There's also an interesting question that relates to a lot of the discussion on dynamic heterogeneity in glasses, where at least a lot of the people who use Lenard-Joseph mixture or something, they tend to find that there is no strong correlation between local density and local dynamics. So the argument that we've been making so far is that there's a very strong correlation. In fact, you can more or less predict from the local density what the dynamics is going to be. At least in these Lennard-Jones mixture simulations that I know of, that correlation is actually very, very weak. Which is why people say you can't look at the structure, you have to look at dynamics, that's how you get the length scale. Okay. So I mean, maybe there is a genuine difference there, but I just thought I'd throw that in the ring because there seems to be a potential difference there.
From the very small fractions we're talking about, because in Lennard-Jones you shear the heck out of it and you get like a 0.2% change in density and a huge change in the mechanical response.
That's right.
So I was talking about the heterogeneity. So if you look at a given configuration and you just try and correlate the dynamical evolution with the local density,
right,
that seems to be fairly poorly correlated.
But I think those changes may be very, very small and may be very hard to discern from the noise.
Also,
the argument that
depends on the range of definition of your local density. If it is a nanometer, probably it is an average that. And atomic level, it may be survive.
I mean, in general, we found
they have looked at it. The people have looked at atomic level or particle level properties, but they've looked at Voronoi volumes and all sorts of things.
Right.
So
I mean, typically we found.
I presume you're making reference to Harwell and Reichmann's work.
Yeah.
They've looked at the first nearest neighbor, next nearest neighbor, next nearest neighbor shell, and couldn't find any obvious correlation with free volume. The message, though, is not necessarily that there's no correlation with structure, it's just that we don't have the right observable because there seems to be something structural about it. Yeah. Otherwise, there wouldn't be that issue of propensity. It's just that. I mean, so that's why they argue for normal mode analysis and whatever else that's correlated with.
Also, density may not be the only parameter.
Yeah, we had a lot more luck looking for local short-range orders, like looking for particular polysomers inside glassy structure that would seem to be much more sensitive than looking at density or things of that sort.
Is there any doubt? What's the evidence? I mean, do we know how big the density fluctuations are in metallic classes?
Yeah. Well, in
from
general,
space, from region to region?
Yeah.
We do?
Well, it's not so easy to detect because in general.
But Tetsu say yes, I want to hear his.
No, you can reconstruct from the first width of the first peak of PBM, which agrees with the model. And model says that the density fluctuation is 6%.
6%.
So that's 6% between the densest region and the least dense region?
No, it's sigma square. So, it's a Gaussian
So the
distribution.
distribution
Right?
of densities has a 6%.
Yeah.
Width.
That's for a very soft potential, right?
12%.
That's for much softer than Lennard-Jones potential.
That's correct. Yeah.
But this is from simulations, you said. Yeah, I guess I need to think about this a little bit more, but I think density on an atomic scale is a difficult. I mean, it's because you need mass and you need volume, and mass is no problem, but the volume is always subjective, I think. So Voronoi polyhedra are probably the most favorite way of doing it, but it's not clear that that's necessarily a right answer.
But from your packing argument, then you would expect the Voronoi signals, Voronoi to give you some signal, right?
Yeah.
Well, you're saying, well, I can look at the local packing structures, Voronoi volumes should show that up, right? We should let the speaker get away.
No, John Peary did this a long time ago, and he said plus minus 4% for hard state. That's a Voronoi fluctuation model.
But I think the question was about density fluctuations, and most of the answer we've heard for modeling simulations, but in terms of an experimental,
that's hard.
That's
you can measure, small atom scattering or something. But again, the density fluctuation varies from one atom to the other. So if you average for soft squares, soft potential, the point is that you have low density regions, but you have high density regions too. It fluctuates both ways. So if you average, over a certain length scale, then this difference is very small. It quickly dies out. So that's the problem.
Yeah, I mean, part of the issue here, especially at least from the simulation standpoint, is to measure any of these quantities like elastic moduli densities. You have to have this some averaging length, and so when you put up a picture like small local regions, hard regions embedded in soft regions, do we have enough hard region that we could actually define that region and give it a continuum property?
Yeah.
It's clear that those regions are large enough to think of them in any way as continuum regions.
Yes, yes.
So anyway, so heterogeneity is what he's raising, okay? Details we don't know, and we still have to discuss research. Yeah, so we still have a job.
Okay.
In fact, maybe the speaker will tell us in the next part of this talk.
Okay, so in summary, so beta relaxation of 1 megahertz is occurs around the glass transition temperature, and this beta relaxation leads to the crystallization of some part of the metal glasses. Then we propose this structure, microstructure. So in order to demonstrate or reveal the validity of this nanostructure, so we have employed the IXS inelastic X-ray scattering measurement and ultrasonic sound velocity measurement. So ultrasonic, in the case of ultrasound sound, so this measures the macroscopic elastic constants, because the ultrasound sound wavelength is very, very long, of the order 1 millimeter. But the phonon, in the case of the inelastic IXS measurements, the phonon sound wavelength is of the order angstrom or nanometer. Therefore, like this, so if the glasses has a intrinsically nanoscale microstructure, so phonon velocity probably should be higher, because the SBR is the SBR sound velocity is much higher, probably higher than the macroscopic average, because this is hard and soft. When the propagation length of phonon is observed, the propagation is probably expected to increase when the wavelength of the phonon is over than the correlation length of this region, domain region. So we have performed the two experiments. One is I used the resonant ultrasound spectroscopy measurement, like this figure, RUS method. From the RUS measurement, so we have obtained we can obtain the resonant spectrum of the elastic medium, so like this. So from this elastic resonant spectrum, so we can deduce the elastic constants of this material. And so phonon velocity, as to the phonon velocity, we have measured the inelastic X-ray scattering, so as the spring gate in Japan. So if this microstructure is realized, so the phonon dispersion is probably should be like this here. So this is the macroscopic average. So the SPR has harder elastic constants. Therefore, the phonon energy, because this is a phonon. This slope is means sound velocity of the phonon. Therefore, the SBR deviates positively. So this is a positive dispersion. So in liquid, the positive dispersion phenomena is frequently observed. But in the case of solid, so the positive dispersion can't be explained so theoretically if observed. So this is IXS spectra obtained for this metallic glasses, palladium, nickel, copper, phosphorus. So this is a low Q and high Q region. And this is a very low Q region. These spectra are obtained for very low Q region. So this this peak means excitation energy of the phonon, and this band width means phonon's lifetime. So okay, and we by fitting the DHO damped harmonic oscillator function to this data, observed data, so we have obtained the excitation energy, and gamma is the lifetime of the phonon. So this is the phonon dispersion relation obtained by for palladium, copper, palladium, nickel, copper, phosphorus metallic glasses. This is the ultrasound line. So please look at these regions. So this is the phase velocity of the phonon and versus wave number. So this dashed line indicates the ultrasonic sound velocity. This is a long length limit. But so as you see, so the sum of part, the elastic, the sound velocity of the phonon exceeds the ultrasonic sound velocity. Therefore, this indicates that the elastic constant of the is higher than the macroscopic average, because the macroscopic average means this value. So therefore, this figure is probably valid, or I think so.
That's only if you assume that this structure has a very well-defined Q, right? For instance, if you have a single delta function, it carries all the Qs. So in this case, the difference between the ultrasound and the X-ray frequency alone is enough to explain the difference. So I'm not sure about the Q value. How valid the Q value is, or how valid to extract psi from this Q crossover. So this object has this Q component. It does not mean that it's the only component.
And also, what would this curve look like in a non-crystallized glass?
Yes. Non-crystallized glass.
No. Yes. This is completely non-crystallized, but it depends on on composition, right?
I'm sorry. So this is a pure amorphous. Pure non-crystallized.
Pure amorphous.
Yes, pure amorphous. Yes. Initial amorphous.
Wait, sorry, I'm lost. It's pure amorphous, but it's one of those glasses that you have annealed under ultrasound.
No.
Okay, sorry.
No.
Okay.
So I guess I'm not understanding exactly what the main point of this is. In some Q range, you're interacting with some local region in the structure, and within that region, it seems to be stiffer than the crystals. So you're getting a higher sound velocity and hence higher elastic constants. But then at another Q range, you're getting a lower sound velocity.
No, I'm sorry. So this is usually as a
that's a dispersion.
Dispersion, yes. Usually in the case of lattice, so I'm sorry, sine curve.
What are we looking at?
And so what are the axes?
Derivative.
I'm sorry.
DC d omega.
So
DC dk rather. D omega dk.
Usually, so
I don't understand what.
No.
EQ. I'm sorry. So EQ.
The bottom is a dispersion relation, right?
Right.
It's energy versus K.
That's right. And then top is the derivative.
Right.
D omega dq.
Right. So it's only a low wave number.
Okay. I'm sorry. So this is a phase velocity.
Yeah.
Okay. So not good.
So why should I be surprised that this
No,
is...
but its value is higher than the Q zero value.
So with the,
Okay.
so the
Okay.
dashed line on the top is the slope corresponding to the red line on the bottom? Is that?
That's red line, but I mean, it's extrapolated.
Isn't that usual? That's the one.
Red line is only the ultrasonic vibration.
The slope.
Yeah, the ultrasound linear.
Ultrasonic, yes.
Slope of the ultrasound linear
Right.
function.
That's what's.
Which is...
But that's corresponding to the blue dash.
Yeah.
Right.
So usually lattice, in the case of lattice, the sine curve. So the ultrasonic, this slope is the highest. So in the case of long wavelength limit. So the ultrasonic vibration, ultrasonic sound velocity is the fastest in the lattice, in the case of lattice. But in this case, so this is not the case. So this, So this is not the group velocity. So this is only the phase velocity. Okay. So E over Q, just E over Q.
Again, my problem is I spend very little time in inverse space. I spend most of my time in real space. So I'm having a difficult time taking the curves on the right and associating those with some sort of structural feature in real space in the curve on the left. Have we not gotten to that point yet, or is it obvious to everyone else but not me?
No, it's not obvious to me.
Oh, okay, so we'll let you go on with the talk then.
Are the Q scales the same, top and bottom?
Yeah, that's where I'm confused.
I'm sorry?
Are the Q scales, are they the same in the top and the bottom?
Same, right?
So
I
how
thought
do
the
I
whole
get
point-
from...
Yes.
I thought the whole point was that with ultrasound you explore a completely different range of wave number.
You see, these are a little bit higher than this line, right? So that's why.
But the horizontal axis is the
I
same
see.
in
Okay,
both.
sorry. None of these results are actually from the ultrasound.
Only lines.
I see.
Yes. Only, yes. Okay.
Data points are-
So only line. Only line.
So the line on the top is the slope of the line on the bottom.
That's correct.
Are the derivatives.
If we plot for the ultrasound, only this point.
Yeah.
Ultrasound. Yes.
Everybody's
Sorry, very confusing. Okay. So therefore, this in that experiment, we probably this strongly bonded region that have the much higher elastic constant. So slightly higher elastic constant exists in the glass substance. Therefore, we have to, in order to this is valid, to check that this is valid. So we have to exclude the time-dependent phenomena. So if some faster process exists between the megahertz and terahertz frequency ranges, so ultrasonic vibrations, elastic constants inevitably lower than the because lower than the IXS elastic constants. So in order to check whether this is absent or present, so we have to elastic constants measurement at low temperature. So for example, this is so usually it's CIJ means the elastic constant, CIJ versus temperature. So usually the elastic constants monotonically decreases like this figure, but when the faster process exists, some process exists, relaxation exists. So elastic constants in the temperature dependence of the elastic constants. So some modulus defects we can observe, like this figure. Okay, so so therefore I have to check whether we can observe this like this or not. So therefore we have performed that low temperature elastic constants from 10 Kelvin to 300 room temperature. So, so we have this is a C11 Young modulus, bulk modulus C44. But most of the elastic constants monotonically decreases, but slightly strong temperature dependent, but not so obvious defect. Therefore, the probably so. Faster relaxation process does not exist in this matrix.
How about quantum process?
Quantum process. So I'm sorry. So for example, mu relaxation or fast beta.
Fast process may be activated with quantum mechanical at low temperature.
More lower temperature.
No, at that, this flattening may be the quantum phenomenon rather than classical phenomenon.
50 Kelvin?
10 Kelvin. That's
10 Kelvin.
No, 10 Kelvin. Two-level systems.
The present IXS and US measurements are at performed at room temperature, so far below the glass transition temperature, TG. TG is in this case 570 Kelvin. So the both frequency regions, megahertz and terahertz, are much higher than the characteristic frequencies of the possible relaxation processes at room temperature. Namely, both frequencies are high frequency, so that the measured sound velocities at such a low temperature means room temperature, by the two measurements don't include any relaxation effects. Therefore, the difference between the two velocities is only attributed to the fact is caused by the difference between their wavelengths. Therefore, so this is a typical characteristic frequency of the palladium nickel copper phosphorus metal glasses. So this is TG is located here, and this is the beta relaxation curve, Arrhenius behavior, and this is the VFT curve, the alpha relaxation. So our measurement temperature is like this point. So far, and the frequency megahertz and terahertz. Therefore, so two frequencies are both high frequency for alpha and beta. I'm sorry. So in comparison to the alpha relaxation and beta relaxation, enough high frequency. Therefore, the time dependent these so. Difference between the difference in the elastic constants between two methods does not include the time dependent. Probably this is due to the wavelength dependent phenomena.
So then, would you expect that if you did experiments at much longer wavelengths, then you might see damping? For example, the beta relaxation is that you pick
much longer wavelengths. So for
much longer wavelengths. Sorry, can I ask another thing that came up at the beginning of your talk? You call this beta process slow, right? But the mode coupling theory beta process, at least within mode coupling theory, actually has a time that diverges at TG. So it looks like it would necessarily be slower than your beta process. So I'm confused by the terminology.
Sorry.
Is that what you call the fast beta process would actually have to be slower than yours?
Beta process is...
Yeah, so this is what you call the slow beta.
Slow beta.
Right. But if I take any mode coupling theory prediction, the MCT beta process will become slower than yours because it actually has a diverging relaxation time. So I'm confused that you can call that one fast.
What did we see?
Sorry?
Diverges at the mode coupling.
Yeah, but they'll diverge somewhere within this plot, which means that the associated frequencies will be zero. So they'll certainly be lower than these ones.
This is confusing.
Okay. Maybe we can't resolve that.
So
Yeah, that's my side of incomprehension.
MCT probe, not an experiment.
Yeah, that's fair enough. Just trying to
No, I
understand
think
the terminology.
yeah. Why is there a reason for dividing it up into 3 different?
So similarly, so we have observed we have performed for 6 types of metallic glasses. So as you see, other than the palladium nickel copper phosphorus, so zirconium aluminium nickel phosphorus, zirconium copper aluminum, and palladium copper phosphorus, platinum nickel phosphorus, and zirconium aluminium nickel copper metallic glasses. We have performed for 6 types of metallic glasses. So this is dispersion relation of for 6 metallic glasses. And this is sound velocity. Sorry, so this is phase velocity of the normalized by the ultrasonic vibration, sound velocity. This one means ultrasound sound velocity. The palladium and platinum and palladium copper phosphorus, namely these 3 metallic glasses. In the case of the 3 metallic glasses, sound velocities of the phonon exceeds ultrasonic sound velocity. And this is propagation length versus wavelength. So wavelength means lambda. So the inverse of the Q.
And you measure the mean free path from the width, from the time? The mean free path is measured from the width of the peak, from the time?
Yes. So I'm sorry. So this bandwidth is at lifetime. Yes. Tau product velocity. Okay.
Gamma is almost linear with Q, right?
Yes, I don't remember that. So I have data. So as you see, so in the case of zirconium case and palladium case, so the V goes right, so the L, propagation length L, increase gradually, and at a certain point, so the increase steeply increase. So this is also the case for palladium nickel copper phosphorus metallic glasses. The phase velocity of the phonon of palladium platinum based glasses tends to exceed, but the zirconium based metallic glasses, so the phonon velocity tends to be close to the ultrasonic velocity, and the propagation length of phonon tends to increase at a certain wavelength. So we try to this phenomenon by using the elastic medium, continuum elastic scattering theory. By using.
Sorry, would you mind just going back to the previous slide? So would you then say that previously you argued that the fact that the sound velocity, the phase velocity extrapolates to above the ultrasound limit is evidence for a length scale. But then would you say that in the zirconium-based metallic glasses, where you never get above that velocity, there is no such length scale and the structure is more homogeneous?
Yes. I like to say more homogeneous.
And palladium glasses are known to be two-phase segregated.
This is
microphase segregated? Okay.
To explain this phenomenon, propagation length, so we have assuming this model. So this blue region is the softer, and this is the hard region. So and the scattering theory is applied. So this is the ultrasonic velocity. So and this is effective phase velocity of the macroscopic phase velocity, and this is diameter. I'm sorry. So this is this corresponds to the Q value. so we can see that the phase velocity increase than the ultrasonic vibration, ultrasonic sound velocities. This point means ultrasonic sound velocity. And so in the case of the L, so propagation length, so the L increases slowly and then steeply increases around the diameter of this inclusions. So this phenomena, this behavior can be very similar to this experimental result.
So are those two lengths consistent? The length scales that you get from the propagation in the experiment?
Experiment.
You get a length scale from the right-hand figure, right?
Yes.
And you get a length scale from Q inverse. Are those the same?
So this is Q, and this is lambda.
You get a length scale from here, and you get a length scale 2 pi over Q from
2 pi over 2 pi over Q.
Are those the same?
Same.
No.
I'm sorry.
This tend to be more larger, right? I mean, so crossover to the left tend to say 1 or 2.
2.
1 or 2 in Q. That's 6 nanometers. Anyways.
I'm sorry. So
I mean, the question was whether the length scale you extract from the change of behavior on the right is the same as the length scale you extract on the left.
This value is like 1.
Okay.
That corresponds to 6.
Oh, okay.
6 nanometer. Yeah.
So those two length scales are not the same.
2 pi over Q.
I don't know.
2 pi over Q. Huh?
Okay, the question is, if I just think of your effective medium picture where they have inclusions of some kind, then both of these effects should be related to the length scale of inclusions, correct? So I'm asking in the experiment, if you measure a length scale from here and a length scale from there, are they the same?
So
the answer is no.
Depends on whether 2 pi is 1 or not.
2 pi is always there. You can register it to be 1. I can.
What do those two lengths look like in your model, in your calculation?
Yeah, maybe go to the model.
Okay. So length scale is not the same. So the experiment.
No, the model. There's only one length scale.
Okay.
Right?
So this is normalized by the diameter.
No, in the model there's only one length scale, the diameter of that object. Right?
Yes.
So everything is related to that length scale. So
also the lengths aren't exactly the same. So on the right, the crossover length is maybe 1, and on the left it's maybe inverse 4 or something.
Yes.
So there is a difference.
So it could be consistent with a single length scale. So even the model doesn't say what you calculate, it's exactly the same. Anyway.
Okay. So we can see the tendency in the calculation. So the sound velocity tends to exceed the ultrasonic velocity with increase in the volume of the soft regions. So red case is a fraction of the soft region is 0.7. So 0.3. So and this is soft region's volume fraction is 0.1. So therefore the increased tendency is higher than with when the soft region fraction is high. So the propagation length of phonons steeply increase around the wavelength exceeding the inclusion diameter without regard to the degree of the elastic inhomogeneity. So all cases we can see the same tendency.
On your yellow plots there, the phase velocity doesn't go down. Is that because you
yes. Yes. Usually, so this, but elastic. Yes, that's right. But in this simulation, so only the elastic continuum elastic. Yes. Therefore, so this cannot be explained reproducibly. So. So we have furthermore we have observed measured the viscosity of the 6 types of metallic glasses. So the fragility of these 6 metallic glasses are listed here. And we have defined that the deviation degree of the average from the average is defined as the elastic inhomogeneity degree of the elastic inhomogeneity. And this the critical point. For example, critical point is the correlation length. Is defined as the correlation length. So we have summarized between the some property. So this is the degree of the elastic inhomogeneity and the fragility. So this is the degree of the elastic inhomogeneity and Poisson ratio. And this is this tendency, the critical wavelength and fragility. So we see that some correlation between these two three properties.
So how do you quantify the degree of elastic inhomogeneity?
So yes, okay. So elastic inhomogeneity is a very ambiguous parameter, but so the maximum value is of the deviation from the ultrasonic sound velocity. Yeah. So, for example, platinum-based metal glasses, this value, and palladium case in this value.
And lambda C you get from the right-hand plot or the left-hand plot?
I'm sorry.
Right-hand plot. Lambda C you get from this plot.
Yes, lambda C. So this is so.
It depends only on one data point. So there must be fairly substantial error bars on the number that you give to the elastic inhomogeneity. No. What is the uncertainty in quantifying that?
How large is your error bar on that determination?
How large? The determination method.
How large is your error? Since you use only one value.
Yes, one value. Yes. So.
Okay. I'm sorry, so before you go to this chart, could you back up just one?
Okay.
So this seems surprising to me. This seems to indicate that the best glasses are those that have the largest amount of inhomogeneity in the structure, which intuitively is different than the way I've always thought of it.
So I'm sorry. So more.
You have palladium, nickel, copper, phosphorus is always near the top. It's near the top of elastic inhomogeneity. It has the
elastic inhomogeneity is Palladium?
Yeah, so the palladium, nickel, copper, phosphorus has a high degree of elastic inhomogeneity. That says that the microstructure somehow is not uniform. And it's more ununiform than zirconium
Zirconium is
or aluminum or So it seems, and palladium, nickel, copper, phosphorus is the best glass.
Best glass.
Forming.
Yes. Yeah.
So these data seem to suggest that the best glasses have the highest degree of elastic inhomogeneity. And this is different than
But why does palladium, nickel, copper, phosphorus have a different degree of elastic homogeneity on the graph on the left than it has on the right?
Yeah.
They're two different. One's Poisson ratio, one's fragility. They're just
on the x-axis.
Yeah, but the y-axis.
The value of the y-axis ought to be the same.
Y-axis. It's down near 1 on the right-hand plot and 1.2 on the left-hand plot.
It appears to be the labels have been swapped on one of those plots.
Yeah, that's right. These two are swapped. PDCP.
Palladium, copper, or phosphorus, and palladium, nickel, copper, phosphorus may have just.
That's right.
And then also, if I can ask a question, this critical wavelength lambda c.
Lambda c, yes.
Is that what you're proposing? Is the length of the strongly bonded region?
Yes.
Okay.
So in our experimental results, so we so in the case of the fragile glasses, so the WBR region is more exists more, so more than the strong glass. So in the case of the zirconium-based glasses, in the case of zirconium-based metal glasses, they are more homogeneous, indicated that more homogeneous. So we have so we want to say that so structural interpretation of glass transition is indicated here. So this is this red line is the entropy or volume. So and this is viscosity. So usually viscosity is increased exponentially towards the TG. So the structure is like a cage structure. So and the orange region is a mobile region and atomic region. And the temperature, when the temperature decreases down, so more strongly bonded regions are gathered, and so the orange regions, mobile regions are fraction is small, and around the glass transition temperature, this is above the glass transition temperature, the weakly bonded regions should be percolated because therefore this is still liquid. But probably this is so exaggerated, but some of part of the weakly bonded regions should be interconnected. And then below the glass transition temperature, this WBR region should be frozen below the glass transition temperature, should be solid-like, becomes solid-like. So this WBR has a very smaller elastic constants in comparison to those of the strongly bonded regions. Therefore, the melting our mobile temperature is very lower than the strongly bonded regions. This is a glass transition temperature. And in the solid, so the beta relaxation can occur in such regions.
You probably didn't mean that the blue line is below the extrapolation, did you?
I'm sorry.
In the amorphous state, the nominal viscosity is infinite. You have a yield.
Ideal.
Below TG.
Below TG.
Once you have a glass, you would expect that the nominal viscosity, so the extrapolation of stress over shear rate to low shear rate, is infinite.
Well, that's by theory, but in experiment, the diffusivity is finite.
But viscosity?
Yes. Yes. So you mean the TK?
How you measure it.
No, I meant so on your graph of viscosity there, did you really mean that the viscosity becomes lower than extrapolated?
Yes. If you measure creep, because
yes.
the structure is frozen.
So usually, we have we define the 10 to 12 Pascal second.
Yeah, sure. So how do you define the viscosity of the amorphous material?
You can measure the change of the, for example, elastic property as a function of the temperature of the glass you will find, and viscosity should be corresponding to the viscosity in the glass in different temperatures.
Probably you mean that TG is TK. At TK, the viscosity is diverse to infinity. But experimentally, we can't reach.
I guess in our definition, at least my definition, a solid has infinite viscosity.
That's right. For theoreticians, okay.
Yeah, so you're talking about a different viscosity here.
No.
But experimentally, if you look at window glass in church cathedrals that are 1,000 years old, they sag, they creep. It's not infinite.
No, because higher. Because of higher.
Because of
But you're saying it's aging.
No, solids don't have infinite viscosity, just very large.
Yeah. It just becomes large, but it's not infinite.
You can just hang a weight on this and then see what happens.
At room temperature, over 10 years, 20 years, 30 years, it'll still creep. If it was infinite, then it would never change shape ever.
But it'll age during the creep, presumably.
Well, you're saying aging, but
But what happens to the flow rate in an experiment like that?
It becomes constant after.
Yes, experimental time scale.
It becomes constant. Right up below TG. If you go too low, it becomes only homogeneous.
So the below the glass transition temperature, the significant change does not occur. Therefore, this percolated some part of percolated regions remains in the glass. So like recently, this is reported by Professor Tanaka. So this is he claims that the dynamic heterogeneity is strongly related to the static heterogeneity. So this is published by 2010, so very recently. So I don't know the details, so the result, and the so simulation treatment, but so this region is dynamics is very active. So and this is a very immobile region.
So here it's a correlation between dynamical heterogeneity with like orientational correlation functions.
So if you want to see the detail to understand, so please see this. So and recently, so this is my not my collaborator, but usually this picture was taken by the Professor Abe of the University of Tokyo. So this usually phase contrast only phase contrast. The amorphous alloys shows this like maze contrast, only this. But he uses STEM scanning stem and Harif method. So he have observed, he could successfully observed by the compositional modulation at a few nanometer of zirconium-based metallic glasses, like this figure.
You expect some fluctuations, yeah, sure. This is beyond the statistics.
Yes, beyond the statistics.
You expect statistically some fluctuation, right?
I guess the question is the amplitude of these fluctuations statistically significant? Is the amplitude of these fluctuations statistically significant, or is that just what you would get from uncorrelated fluctuations?
Just randomly distribute these atoms. Of course, you have some fluctuations. So is this more than that random fluctuation?
So probably this Harif stem in the Harif stem method. So the bright field, bright region indicated that the heavy element. Because this indicated that the platinum-rich regions.
I think the question that they're asking is this. When you look at this image, you look at the bright region and the dark region, and you think, oh, there's a huge composition difference. But we don't know what...
So very slight.
Maybe it's 50% here and it's 49.8% there. Or maybe it's 50% here and 20% there. We don't know. Can you tell us what the difference in composition?
That's a contrast.
Yeah, what's the contrast? Because you can change the contrast and make it look as dramatic as you like.
Okay, yes, that's right.
Is that information available in the work that this professor did?
Yeah, so this is a very slight modulation, compositional modulation. Therefore, the threshold of the deviation is very important. So it is difficult to clearly exist as a compositional modulation in the STEM. But from his experience, he claimed, he judged that this is a compositional modulation exists in the glass.
I'm just looking at the length scale here, maybe 2 to 4 nanometers, and that seems intriguingly close to the length scale that you predicted from your other work, which was, I think, 3.5 to 5 nanometers. Is that just coincidence?
Yes. No. The system is not different. So this is a zirconium. So
this one didn't have that other length scale, right? The zirconium-based glasses didn't have that other length scale. Shorter
wavelengths. So correlation length.
I thought the zirconium ones didn't have this inhomogeneity that you were talking about before.
I'd like to say that zirconium is a more
it was farther down.
More homogeneous. So.
Zirconium.
Well, for the zirconium, the velocities didn't even go above ultrasound, so it was hard to extract the length scale.
Yes. So if it happened, it happened. That.
This.
Right. So here you said the zirconium did not do it.
In the zirconium case, this is a.
But here zirconium, copper, aluminum. The last.
Yes.
Zirconium, copper, and
platinum.
It's completely different.
So slightly different. Therefore, so exact not exact match, not much, doesn't match. Okay, so summary of the static heterogeneity. So from ultrasonic experiments, our experiments, the beta relaxation locally occurs, not homogeneously. The beta relaxation eventually deteriorated the glass structure. And from the partially crystallized structure of palladium, nickel, copper, phosphorus metallic glass, so glass is considered to consist of SBR and WBR. This is still under debated. So from low temperature dependence of the elastic CIJ, fast process, for example, lateral motion does not occur, does not exist. From IXS and ultrasonic measurements at room temperature, in which there are not any relaxation effects. So nanometer wave sound velocity exceeds millimeter wave sound velocity strongly indicated that the nanometer scale elastic inhomogeneity, static heterogeneity. And the nanoscale elastic constant fluctuation is evaluated from the phonon propagation length and deviation of the macroscopic elastic CIJ.
Can I just ask you about your middle point there? I mean, you say there's no rattling motion, but I thought all you had shown was that there is no process that freezes over that time interval. So is it not possible that the rattling motion is present throughout that entire temperature interval? I mean, how do you know that it does not occur? I thought you had only shown that there is nothing that changes in that temperature range. Is it not also conceivable as an interpretation that the rattling motion is there at all of those temperatures?
Rattling motion?
Yeah, I haven't grasped why you say it doesn't occur.
Yes. So I have measured low temperature elastic constant measurement. So we have not detected the anomaly of the normal temperature dependent of the elastic constant. Therefore, we may conclude that so if the
so you think at some point the temperature will be low enough that it should
below yes below.
Lots of ultra low temperature measurements which shows dependence.
So this is the last part. So many remaining issues. So what is the glass transition? So more. This is so I like to grasp this more physically. So if the correlation length exists, so what is the origin of the correlation length? So this is only this is from the is this indeed from the thermodynamically? So I don't know. So if you static you have any idea, so please consider. So the how are the complicated relaxation process related is inhomogeneous structure. So can you so explain with mode coupling theory? So and why is such an inhomogeneous structure formed? So this should be I like to understand with using the statistical thermodynamic viewpoint. And I have to make efforts to the consistency with the other models, so etc.
We all agree with the heterogeneity, although interpretation is heterogeneous.
Are we asking questions? So I have a question. So you conclude that there is some characteristic length scale of inhomogeneity. Now, I've come across a term in the literature just recently that I don't understand. It's called coherent scattering domains, CSD. And the length scales that they report are similar to the length scales that you report. 1.5, 2 nanometers, 3 nanometers. Is anyone here familiar with this term, coherent scattering?
Fluctuation microscope?
Well, I don't know how they obtain. I don't think so. I think they get it from standard X-ray diffraction.
Must be this fluctuation.
Well, I'm almost certain that it's not fluctuation microscopy because some experimentalists gave me this information, and I know that they have no access to fluctuation microscopy.
Depends on how it is defined.
Yeah, so I don't know how it's defined and what it means. I'm just wondering if this is a common term and if people have seen it in the literature and if they know how it's obtained. I'll ask the folks who give us some information.
So So usually, so as you said, so it is difficult to observe the heterogeneity in the microscope. So but have you ever used the STEM hard?
I haven't personally, but we have such a unit, and I know people who use this.
But historically, when people use the width of S of Q,
Yeah.
then you get 1 or 2 nanometers in E.
I will just make a comment, and this is a provocative sort of comment. But when we look at these length scales, let's say 2 nanometers, if you look at an atomic cluster, that's the central atom, the first shell, and maybe the second or third shell. And if you look at the diameter of that, it's the length scales that you're talking about. So these aren't really big extended domains. They're clusters with 2 or 3 shells.
That's right.
And it's if you look at the icosahedral or quasi-crystalline community, they have very elegant approaches for showing how you can develop icosahedral-based clusters that pack out actually to the 3rd, 4th, and actually out to the 6th shell.
Sure.
With very efficient packing. And so these length scales are maybe not surprising if you consider an efficiently packed cluster that also has either kinetic or energetic motivation for building a 2nd or 3rd shell, and where you can retain efficient packing. Then these maybe make sense. And then your weakly bonded region could just be that you have one cluster here and another cluster here, and they don't have orientational order. And so you have this region of packing frustration in between. It's a simple and probably provocative concept, but it's maybe worth thinking about.
What determines the size?
Yeah, I think there are many things. Of course, you have to look at the thermodynamics, statistical mechanics, configurational entropy, bonding energy, and topology. But yeah, I think you have to look at all of them together. And to my knowledge, no one uses all of those views together. Many of us in the room use 1 or 2 views, but taking all of those views together, I think, may have some value.
We talked earlier about whether there are other ways of measuring the length scales of these density fluctuations. Is there no practical experimental way of just measuring S of Q?
SQ?
Yeah.
Yeah.
Factor.
Oh, yes. I have measured SQ. I have measured.
And what length scale do you extract from that? Is that the same length scale as you get from here?
So.
That's easy.
Not. Yes. Yes.
That is quite dense compared to other classes.
But when you get the total SFQ, there are 2 ways of analyzing the data, right? There's the Baccia-Thornton approach, and then there's, I forget what the other one is. But one of them gives you composition.
But that's feasible only for binary.
Only for binary.
Beyond that, it's just impossible.
And what length scales do people get in binary systems?
Well, it varies.
But are they in that sort of nanometer ballpark?
Yeah, exactly. Usually the correlation peak shows up at 1 inverse angstrom, around that.
I'm sorry, around 1 inverse?
Inverse angstrom in Q.
Okay.
That's the population correlation function.
So 6 angstrom or something, that's still a bit smaller than these ones.
I'll just mention this. You said beyond binary it's essentially possible. We're just writing up a paper now where we've attempted to calculate the partial fraction.
No, for model calculation you can do that. But
This is experimental. So, we can talk about this later. It's very, very difficult, and we've run many experiments. But we can talk about it now.
But can't you, from your structure for the binary, from your theory for the binary packings?
No. It's an experimental.
Sure, but if you took your theory for the binary packings and you said, okay, I'm going to pack those clusters roughly randomly the way you described, can you not work out what the S of Q is for the density and the composition fluctuations?
You'd have to put some additional details in it that I haven't. You have to put the statistics in, which I haven't.
But if you see that there's like a liquid structure for the clusters or something.
Basically you just define the length scale as the inner cluster separation, and it's on this length scale. It's about an inch.
Yeah, fair enough.
Good. Everybody agrees that the system is not completely homogeneous. Thank you.
Thank you very much.